My name is Paul Magner. I'm a professor in the Cognitive Information Sciences group on behalf of the Distinguished Cognitive Scientists Committee, Colin Holbert, Peter Van der Trapp, Dean Matlock, and myself. I welcome you here today, and it is my pleasure to introduce Professor Lawrence Larry Barsalou, recipient of the 2018 UC Merced Distinguished Cognitive Scientist Award. Larry Barsalou is a professor of psychology at the University of Glasgow and the Institute of Neuroscience and Psychology. He received a bachelor's degree in psychology from the University of California, San Diego in 1977 and a PhD in cognitive psychology from Stanford University in 1981. He has held faculty positions at Emory University, the Georgia Institute of Technology, the University of Chicago, and then he joined the University of Glasgow in 2015. This is the 11th year of the Cognitive Information Sciences Department has given this award. Previous winners were Mahzarin Banaji, Olaf Sports, Daniel McNamara, Dana Ballard, Helen Neville, Michael Turvey, Pat Churchland, Mike Mosier, Linda Smith, and George Lakoff. The award is funded by the Department of Cognitive and Information Sciences and by a generous gift from Bob Blushko and Pamela Samuelson. And when I was writing this up, I realized that the award and the gift have strong ties to UCSD. Neville, Mosier, Churchland, and some of us in the department all have been affiliated with UCSD, as was Bob Blushko and as was Larry. In fact, if I recall correctly, Larry worked as an undergrad in the same lab as Bob worked in when he was a grad student at UCSD and participated in some of the key experiments there in the early 70s with Dave Rumelhart and others when they were basically inventing cognitive science. But more about Larry. He has held a Guggenheim Fellowship and has served as the chair of the Cognitive Science Society. He is a fellow of the American Association for the Advancement of Science, the American Psychological Association, the Association for Psychological Science, and the Cognitive Science Society. He's also a fellow of the Mind and Life Institute and the Society of Experimental Psychologists. And I'm proud to call him a friend. His research addresses the nature of human conceptual processing and its roles in perception, memory, language, thought, social interaction, and health cognition, as we learned about earlier today. A current theme is that the conceptual system is grounded in situated conceptualization, multimodal simulation, and embodiment. And it is our great pleasure to have him here today to hear him speak on grounded cognition and situated action in multimodal simulation, and to present him with the 2018 UC Merced Distinguished Cognitive Scientist Award.
Thanks for the wonderful introduction, Paul. It's a pleasure and an honor to receive the UC Merced Award for Cognitive Science. Being a product of the UC system, it's especially a pleasure to receive this award on UC campus. Because I'm also a product of the international cognitive science community, it means a lot to be recognized by the fine cognitive science community here at Merced. Over the course of my career, I've been most fortunate to have been trained, mentored, and supported in numerous ways by our modern communities in psychology, cognitive science, and neuroscience. My abilities and work reflect myriad influences from thousands of talented, committed, and productive researchers in these communities, and the great work that they produce. I'll do my best to make a small fraction of these influences apparent in this talk, and will hopefully convey a sense of the impact that they've had on me and my work. So today I'm going to be addressing the nature of human cognition. Well, by cognition I mean the processes that make humans intelligent and allow them to act effectively in both physical and social environments. Typically, cognitive scientists assume that cognition results from processes that include things like attention, perception, language, emotion, and so forth, with these processes supporting all forms of intelligent behavior, ranging from navigation to consumption to social interaction, decision-making, and so forth. A tremendous amount of work in psychology, cognitive science, and neuroscience has focused on these individual processes, and we know a lot about them from this work. Other work, however, has asked more general questions like, what's the best approach to take in understanding cognitive processes? And how can we best describe the general architecture of the human brain that underlies these processes and makes them possible? I want to begin with some of these more general questions before turning to specific processes. So one important framework for understanding cognition is Mar's classic levels of explanation. According to Mar, to fully understand a cognitive process, you need to understand it at 3 levels. First of all, you need to understand it at the computational level. And what he meant by this was you need to understand the tasks that are associated with cognition, whereby the task meant stimuli that an organism or a person encounters, behaviors they produce in response to those stimuli, and the rules, laws, principles that govern the relations between stimuli and responses. A good way of thinking about this, I think, is that it's explaining what's going on in the physical world in association with the cognitive process. But Mar further argued at the algorithmic level, you also need to understand the processes within an agent that allow the agent to perform the task as I just described. Typically in cognitive psychology and cognitive science, the classic forms of these algorithmic processes or mechanisms associated with representations of processes, although other possibilities exist as well. And then finally, Mar argued that these algorithmic mechanisms need to be implemented and understood in some kind of physical manifestation, which could include a biological organism, an artificial agent, and so forth. Mar also argued, besides proposing that we need to understand the cognitive process at all these levels, that a full explanation requires an integrated account across all of these levels, how all the levels of explanation work together to produce a process. Although there are good arguments for why all 3 levels are essential for good scientific explanations, there sometimes can be a strong proclivity to bypass explanations at the algorithmic level. In psychology and cognitive science, for example, purely behavioral approaches exist that offer laws and relations at the computational level without offering accounts of the algorithmic mechanisms that implement or produce these relations. Similarly, in neuroscience, work often bypasses the algorithmic level as well, specifying stimuli and responses in the environment, and then mapping them directly into biological substrates without really specifying the mechanisms that make this mapping possible. So, given the importance of algorithmic mechanisms in complete accounts of cognitive processes, it's also useful to think about what is the best approach to take in trying to account for these mechanisms. Perhaps the classic approach in cognitive science, cognitive psychology, is what is often caricatured as the sandwich model, which views cognition as a module, standalone system in the brain, similar to standalone systems for perception, action, affect, and so forth, with cognition not relying on systems in perception and action for its functionality, and primarily just using perception as a way to get information into the cognitive system and the action system. Cognition doesn't depend on these other systems for what it needs to do. In contrast, an approach that I've worked on, along with many other people, offers a significant alternative to the sandwich model. I'll refer to it here as grounded cognition, but often it's referred to as embodied cognition or situated cognition. The central assumption of grounded cognition is rather than cognition just being a module that contains mechanisms like these, instead cognition intrinsically relies on mechanisms in other domains. In particular, in the modalities, it utilizes representations and processes in things like vision and audition, taste, and so forth. It also relies on mechanisms in the body, especially mechanisms associated with action. And then it also depends critically on the environment. So following Gibson's pioneering ideas about the importance of coupling perceptual systems with the environment, that it makes no sense to try to understand perception without understanding the coupling with the environment. Situated cognition makes similar assumptions, that to understand cognition, we need to understand how cognitive processes are coupled with the physical and social environments. So the idea from the grounded perspective is that cognitive processes emerge from interactions across all of these domains that are not localized in a single module. Another central theme of grounded cognition is the important role of action. From this perspective, cognition doesn't operate in a vacuum, but instead primarily serves to support organisms in effectively implementing goal-directed action in the environment. One way of characterizing action is via something I'll refer to as the situated action cycle. The idea that this cycle captures, I'll go through it in a little bit more detail in a second, is something that has been central to theories of psychology and cognitive science for decades. In many ways, you can see classic theories of conditioning and behaviorism as being very concerned with the situated action cycle. The environment cues behaviors, which produces reward. But it's also been central to more cognitive theories, such as Newman and Simon's theory of problem solving, Miller-Glenter and Prebram's theory of action and planning. The situation action cycle is also central to many theories of narrative and text, especially when they talk about how we represent and process events. So the basic way the situated action cycle works, as I'm characterizing it here, everybody characterizes it a little bit differently, is that something occurs in the environment, some kind of entity or event that takes place, which then produces a cognitive state in the organism, which essentially constitutes capturing how what's happening in the environment is relevant for the organism. These states can include things like activating goals that the organism might pursue, values, norms, identities, and so forth. As self-relevance is established about what's happening in the environment, this can in turn produce affect, which could include both motivation and emotion. In turn, affect can trigger various kinds of actions, ranging from overt actions in the environment to executive actions in the cognitive system. And finally, these actions can produce outcomes in the environment that change the environment, such that now the organism is in a different situation, and the whole cycle iterates again as the organism continually interacts with the environment. I've laid this out as a holistic kind of linear sequence here. I don't think that actually works like that. This is just for communication purposes. It's probably much more complicated and parallel than this. But this is the basic idea of what I'll be meaning by the situated action cycle. Interestingly, the situated action cycle links together all the domains of grounded cognition that I talked about a moment ago. So here are all those domains represented somewhat differently now. Here you have the cognitive mechanisms, the modalities, the body, and the physical and social environment. And the situated action cycle links them together in the following way. Things occur in the environment, entities, events. Here, they in turn trigger self-relevance responses in the cognitive system. These self-relevant responses produce affect. Affect produces action back out into the world, and these actions in the world change the environment. So the situated action cycle, so it's perhaps not surprising that the domains of grounded cognition that I went through before are a part of grounded cognition, because they're all necessary for the situated action cycle. Interestingly, the situated action cycle also offers a nice way of providing the integration across Mars level that Mara argued was important. So the environmental action and outcome phases of the situated action cycle can be viewed as providing an account of what's happening at the computational level in the world. The implementation level can be captured by the body or the physical nature of the agent that is computing self-relevance and affect and integrating action. The algorithmic level can be viewed as trying to explain the mechanisms within the physical implementation that make intelligent behavior possible. And then if we embed the implementation level and algorithmic levels in the computational level, we have the integrated, we have the integration of Mars 3 levels that he argued was important. So from within this general framework, I'm going to start focusing on the kinds of work that I've done from this perspective. And basically the focus of my work has been on the nature of the algorithmic level, of the mechanisms at the algorithmic level that essentially make the situated action possible and that result from operating it in the environment. And the framework that I'll be working with is what I refer to as the situated conceptualization framework. And the basic theme of this framework will become a mantra over the course of this talk is that cognition adapts itself to situations. And basically, maybe another way to think about this is that cognition is not a context-independent engine, like in modular views, and that there's no such thing as the cognitive system. Instead, the brain and the body offer a set of resources that can be soft assembled to implement specific cognitive apparatuses that then operate in the environment to implement the situated action cycle. And I'll flesh this out further in the next few slides. So there are three core assumptions of this view. The first is that the various kinds of behaviors, especially the habitual behaviors that organisms engage in over and over again, constantly engage the situated action cycle. So tool use, consumption, emotional responses, all of these different kinds of events engage the situated action cycle as I just described. Second assumption is that each engagement of the situated action cycle soft assembles the relevant resources in the brain and body that are needed to execute the situated action cycle in a specific context. And I'll refer to these soft assemblies of resources as situated conceptualizations. And essentially, this can be viewed as the brain and body implementing a cognitive system that is adapted to the current situation so that the situated action cycle that the organism wants or at least wants to try to implement can run in the current situation. The final assumption is that once a situated conceptualization has been soft assembled and run, it gets superimposed on the brain, such that a record of it becomes established in memory, which later allows some expertise in assembling the situated action cycle in later situations, such that the organism doesn't start from scratch. Okay, so this is just to give you a sense of what I mean by assembling soft assembling resources in the brain. And so the idea is that the brain is a collection of resources that can be used to implement the situated action cycle, where each resource can be viewed as a distributed network throughout the brain that performs a specific function, such as recognizing the setting that you're in or recognizing objects. So things that process the situation of the environment. Other resources establish sort of the self-relevance of what's happening in the environment, such as goals, which can in turn produce various affective states, such as motivations and emotions. In turn, these can engage various kinds of resources for implementing action. And in turn, once action has been implemented, there are other resources that process the outcomes of the world in terms of, say, reward, surprise, expectation, satisfaction, and so forth. But the idea is that whenever the situated action cycle runs, it's drawing on resources like these. Not all of these might be active at a given run of the situated action cycle. And in each run of a situated action cycle, the networks that are used are driven into specific states that can vary widely across uses of the situated action cycle. So the idea is that after tremendous amounts of experience of performing situated action in the environment, many situated conceptualizations become superimposed on memory, such that the organism has a collection of the soft assemblies that it has assembled to perform the goal-directed action that has been important in its learning history. And we assume here that different individuals will have very different collections of situational patterns of memory because different individuals have different situational experiences, therefore they have different learning histories. And this is going to cause them to behave differently in the future, given the next steps of this account. So we assume that the organism brings this collection of situated conceptualizations into each situation it encounters with the external situation, then sort of queuing out the situated conceptualization that provides the resources best suited to operating within that situation. In addition, the organism's current state is important as well, and queuing out the best suited situated conceptualization for the current situation. But the idea is that given the current situation, both external and internal, the best fitting and situated conceptualization is active, which then essentially implements that collection of that soft assembly of resources to help process the current situation. So it's essentially adapting cognition to the current situation by finding a good fitting situated conceptualization framework. So again, we view this as adapting cognition to the current situation, and we assume that the basic process that's running here is that as the situated conceptualization becomes active, it starts implementing its resources in the brain, that it's essentially performing pattern completion inferences. It's going beyond the information it started with and preparing the organism to do all sorts of things that have been encountered in the past in this situation. And these can include things like interpreting the situation, generating all sorts of inferences such as likely outcomes, and then organizing behavior in order to achieve those outcomes. Okay, so what I'm going to do for the next section is to review evidence for this account. And so the basic point that I'm going to be making with these examples of literature from my own and other people's work is to offer evidence for the fact, for the idea that what the brain is doing is essentially creating sort of adapted cognitive systems for handling specific situations that a person finds themselves in. And so I'll start with action, and with a classic experiment from Alex Martin, who's one of my heroes and mentors, taught me how to do neuroimaging, amazing work. And this is a classic experiment from his group done in 2000, where they simply presented people with pictures of tools, buildings, animals, and faces. And in some experiments, participants just looked at them for 3 seconds, and others they named them, but they were just shown briefly for 3 seconds. Participants really didn't have to do anything except lie there and look at the pictures. And what they found is that when people looked at the tools, the left hemisphere grasping circuit became active. This is a circuit that if you actually reach out and grasp and manipulate an object, would be used to implement that action. These are all right-handed participants, and so this left hemisphere network controls their right arms and hands. And so basically what appears to be going on here, and the way they interpret their results, is merely looking at a hammer activates the situational pattern of the relevant resources that you would use to interact with the hammer, such that the brain is organizing itself to kind of handle the kind of situation that you would find yourself in if you had encountered it. There are many related findings, both behavioral and neural, showing the same kind of thing, that when you encounter a tool, in a sense, what you're doing is computing the affordance of the tool, and you're anticipating with all the relevant systems of the brain and body. This next example comes from the eating literature. This was an experiment that, from my lab done with Kyle Simmons and Alex Martin. This was the first experiment where he was teaching us how to do these kinds of experiments. And this is just simply, basically a knockoff of the experiment we just looked at. Essentially, it's the same kind of experiment, except done with foods instead of tools. And what we did was we presented people with pictures of high-fat, high-caloric foods mixed in with pictures of buildings. The participants' task was just to look at these pictures for 3 seconds and press a button whenever they saw a repeated picture, which hardly ever happens. So they're just looking at these pictures. But what we predicted would happen based on the experiment I just showed you was that people would activate situational patterns in memory associated with eating these foods. And they would activate these situational patterns, which are essentially records of resources soft assembled to eat particular kinds of food. And then as these resources became implemented in the brain, they would start producing inferences about eating the food. And that's exactly what we found. So this red dot here it represents an activation found in the right hemisphere, in the right insula, right frontal operculum. This turns out to be the primary taster in the brain, both on the left and the right. All of these other little markers are from experiments where participants actually tasted things in the scanner, where liquids were dripped into their mouth, and these are areas that became active whenever they tasted something as opposed to when they did. And our activation both right in the middle of all these, as you can see over here, Interestingly, though, our participants aren't tasting anything. They're just looking at a picture. And yet they're activating this taste area. And so and this fits our prediction that when they looked at a food picture, they would activate the asituated conceptualization that's been established on eating, say, a brown meat in the past. And this situated conceptualization would come active and generate a taste inference. We also found that looking at these pictures generated reward inferences as well. So this red dot here is an activation we found in an area associated with food reward and other kinds of reward as well. So participants were not only anticipating the taste of food, they were also anticipating its reward value. Since this original study, many similar studies have been done, and they've replicated the activations in these areas robustly, demonstrating that basically the brain, whenever it sees a picture of a food, is preparing itself to act in a situation where that kind of food is found. So the next example I'm going to show you comes from emotion. So the two experiments I've shown you so far manipulated cues in the external situation, pictures of tools versus buildings, foods versus buildings, and so forth. And then looked at what happened when relevant situated conceptualization became active and produced activations in other areas that would be viewed as resources associated with processing that kind of object. This next study, we're going to take a different strategy. We're going to hold things constant in the external situation. We're going to have two groups of participants. Each group is going to get the same critical stimulus, the same cue, which is going to be either the word fear or the word anger. We're going to be asked to generate an emotion to it. What we manipulate through training are the situated conceptualizations that participants establish in memory. So the idea is that if people have different populations of situated conceptualizations in memory, then when they get the same cue, they're going to activate different situated conceptualizations, they're going to soft assemble different resources, and people are going to experience emotion differently. So this was work done with Lauren Dubois, former grad student. And basically, the work was addressing the nature of emotion, how emotion is implemented in the brain. The standard view of emotion at the time, and still to a large extent remains, that emotions result from innate circuits that have been delivered evolutionarily to our brains. So we have an innate circuit, say, for fear, disgust, anger, and so forth. And every time you feel an emotion, you activate the same circuit. An alternative view, which Lisa Feldman-Barrett developed, in which we worked on together for a long time, is that emotion results in a very different way from what's proposed by these innate circuits. Rather than emotion activating a circuit for, say, disgust or fear, what the brain does instead is to soft assemble resources that are relevant for generating a specific form of an emotion like fear. So, for example, imagine that you're at a dinner party and you say something really stupid and everybody's starting to scowl at you and you feel embarrassed. What we would argue is starting to happen is that certain resources in the brain are processing the external situation, what's happening out there in the world. Other resources are generating internal states and processing their internal states, say associated with arousal and valence and all sorts of other things that can go on in the body during emotion. And then finally, additional resources become active that help deal with the situation, both cognitively and motorically. Maybe something you say, or maybe you leave the room, or whatever. But the idea is that every time you're in an affective situation, you soft assemble the processing resources you need to sort of handle it, and in the process, emotion gets generated. And as a result, what happens over time, after experiencing fear many times, many different situated conceptualizations become associated with your fear experience. And what kind of holds them together is the fact that we all refer to them with the same word, fear, such that that's what causes the fear to become a category. And then finally, there's the assumption that to the extent that people experience different fear situations, they're going to produce different states of fear because they're going to soft assemble different resources. And that's basically the intuition that motivated this next experiment. So what we did in this experiment, there was a training phase and a test phase. And in the training phase, we created different populations of situated conceptualization, two groups of participants' memories. And then both groups came into a scanning session where we gave them the identical cues and looked at whether their training experience caused different neural states to result in response to the same cues. So in the training phase, one group of participants, the physical harm condition, the physical threat condition, received situations involving potential physical harm, such as almost getting run over while trying to cross a street, where they were asked to immerse themselves in the situation, imagine it happening, and then to generate a state of fear in that situation, or in other trials to generate a state of anger. So one group generated states of fear and anger in these physical harm situations 83 times over the course of learning. And we assume that each time this engages the situated action cycle, lays down a situated conceptualization, such that these 20 participants are establishing a large population of situated conceptualizations and memory associated with physical fear. The other group of 20 participants received social evaluation or social threat situations, such as saying something silly at a dinner party. And again, we're asked to generate either a state of fear or a state of anger on each trial, and they too did this 83 times. So we assume that after the training phase, participants have very different situations stored in memory for fear and anger in those two groups. They then go into the scanner, and on each trial, they get a word such as fear or anger, and there's some other control trials I'm not telling you about, but they basically get a word and they're asked to generate a state of fear or anger, and then a situation is presented, one of the ones that they studied earlier, and they're asked how likely would it be to experience that state of fear or anger in that situation. The key thing is that in the imaging that we did, so the cue word is up there for 3 seconds, they generate a state of fear or anger, and then the situation appears. In the imaging analysis, we only looked at images from the 3 seconds when the cue appeared, and we removed all of the activations associated with the situations, using what's called the catch trial design. It's a really powerful way to separate the activations from sequences of stimuli and imaging. And so what we were interested in was, even though both groups, both the physical and social groups, were getting the word fear, were they generating different patterns of neural activity during this 3-second period for the situation? And this slide summarizes the results. The red areas here are areas that were active for the physical condition. The blue areas are active in social condition. The green areas are areas that process the auditory stimuli in the experiment. And yellow represents an overlap. As you can see, there was very little overlap in this experiment between the two groups. So on an average, 14% of the box was active for a group overlap with the other groups. So very little overlap in activity in the brain for physical fear versus social fear. And again, the way that we interpret these results, so what's happening in these two groups are assembling very different sets of resources related to either experiencing physical fear or social fear, such that when we actually probe their brains and they're generating states of fear, neural activity looks very different. Next, I'll turn to abstract concepts. And the sort of the central issue that this work addressed is, how do we represent abstract concepts? I think this is one of the things we know the least about in cognitive science, and it's a really hard problem. We know a lot about how we represent concrete concepts, but much less about abstract. One classic account of how we represent abstract concepts is Dualcode theory, which basically proposes that the way we represent abstract concepts is with language. So if you take an abstract concept like estimation, it's really hard to come up with an image for that, at least right away. And so maybe it sort of follows from this perhaps that we don't really have sort of sensory motor representations of these concepts the way we do concrete concepts. And so instead we represent them with language because we can sort of talk about them even if it's not to image them. Perhaps the strongest evidence for this view comes from research in cognitive neuroimaging. that has compared the neural activity for concrete and abstract concepts. So in these experiments, participants receive concrete and abstract concepts randomly intermixed, the brains are imaged, and then just as sort of an average image of the abstract concepts is constructed in concrete, and then of interest is what areas are unique for abstract concepts. The important thing about these experiments is typically they all involve very superficial processing of the words associated with these concepts, such as doing a lexical decision task, a triad similarity task. There's really very little attempt to dig into the semantics of these words. So what this figure shows here is a meta-analysis of many experiments of the type I just described from Jeff Binder's lab in Wisconsin. And what it shows, as similar to other reviews and meta-analyses, is that abstract concepts heavily engage the left hemisphere, at least in these kinds of tasks. So we see activation in frontal areas and the temporal areas, consistent with the idea that language is central to processing these concepts. Now, a very different kind of theory about abstract concepts is something that Paul Schwanenflugel developed a long time ago, known as context availability theory. What this theory proposes, very similar to the situated conceptualization framework, is that background situations are central for all concepts, not just abstract concepts, but concrete ones as well. So the idea would be, say, to understand a concept like hammer. You can't understand the hammer by just looking at the object. You need to know how the object is used, and what kind of action it is engaged with, what kind of goals it's supported, what kind of outcomes result, and so forth, before you really understand what a hammer is. And so Schwanenflugel argued that all concepts, both concrete and abstract, depend on context in this way. But she also argued that abstract concepts especially depend on background context, because their semantics are often distributed all over a situation and are not nearly as localized as, say, the way hammer semantics are. Or at least sort of there's a focal object, and for many abstract concepts there aren't these kinds of focal parts of the situation that can be easily identified. So we've attempted to further develop context availability theory, making a couple of proposals. One proposal that we've made is that one thing that distinguishes abstract concepts, and it's part of their semantics, is that abstract concepts often refer to internal states of the organism, and this is why they're not concrete. Concreteness is often defined as being in the extra world. And perhaps abstract concepts aren't concrete, they're abstract because they're referring to things inside of us like goals, emotion, mental lives, and mental operations, and so forth. Another thing that we've argued, especially recently, is that abstract concepts are important for integrating situations. They often tie together elements of both the external situation and the internal situation to sort of explain how all the different parts of the situation are related. And again, we believe that this is true for both concrete and abstract concepts. So this next experiment that I'm going to show you is designed to test some of these ideas. This is work done with Christine Wilson, Mendenhall now, who was a former grad student at Allison, and again Alex Martin. And the idea behind this experiment is what happens when we situate abstract concepts rather than just processing them say, in a lexical decision task superficially. We get people to process them deeply with respect to situations. What do we see happening in the brain? And so we developed a novel paradigm, which is illustrated here. So what we did in this experiment, people only saw two abstract concepts, convince and arithmetic. And they also saw two concrete concepts, read and roll. And the way the experiment worked was these four concepts repeated over and over again in the scanner, randomly ordered. And after each concept, at least on some of the trials, a picture would appear, and the participant would have to say whether the concept applied to the situation. So convince applies to this pitching situation where the manager is trying to convince the pitcher of something. Arithmetic applies here because this person's measuring something. So basically, 25% of the time, the situation was relevant to the concept, and people would press a button to say that it was relevant. The other 75% of the time, the situation wasn't relevant. But our thinking was that what would happen would be by sort of pairing these abstract concepts with situations where they were relevant. I believe there were like roughly 25 situations for each of these concepts. So a lot of different kinds of situations for convince and arithmetic. There were also situations for read and rolling. But the idea would be that by pairing convince with these situations, it's activating resources in the cognitive system that are relevant for processing convince in situations so that people can figure out whether convince applies to each of these words. And so we predicted we would see very different patterns of activation in this experiment than in the classic experiments. The other thing we did in this experiment is we had localizers at the end of the experiment, where for these two concepts, for convince, we showed people pictures of people, and we asked them what they were thinking to kind of find the brain areas that are associated with social cognition, mental states. And for arithmetic, we had people perform various kinds of numerical operations with parts of the brain. And so we were interested in whether the brain areas active for convince and arithmetic fell on the areas established by these localizers. The other thing I should tell you about this experiment is that we again use this catch trial design that we're so fond of, which allows us to separate the activations for convince and arithmetic from the pictures that follow. So the data I'm going to show you are only activations in the 5 seconds when convince and arithmetic were up before the picture appeared, and the activations from the pictures have been removed. So this slide summarizes the key results. Up here at the top are in light blue are the areas that the sort of social cognition localizer identified, and the dark blue regions are activations that were more active for convince than arithmetic. And amazingly, all the activations for convince fell within the localizers for social cognition and didn't fall outside the localizers. So basically what this suggests is that when people represent the semantics of convince, they're simulating the kinds of processes that are involved in representing other people's thoughts. And the same thing occurred for arithmetic. For arithmetic, we found areas in the interparietal sulcus associated with magnitude and numerical processing that fell within the activations established by the localizer for numerical processing. So basically what this experiment shows is that when you ground abstract concepts in situations, you get very different patterns of activation than you do in an experiment where you just process a word superficially. You actually see the resources that are relevant for processing that abstract concepts in relevant situations. Two other interesting findings from this study. First of all, very few left hemisphere activations for convince and arithmetic. In fact, read and rolling had more left hemisphere activations than did convince and arithmetic. The second thing is there were more occipital activations for convince and arithmetic than there were for read and rolling. Something we found in other experiments as well as abstract concepts. They often activate visual areas, tunneling. So the point again is you get very different results for abstract concepts when you situate things. So to just take this idea a little bit further, that wording depends on situations. This next slide shows sort of a classic line of work which demonstrates the effect of situations on any kind of word meaning, not just abstract concepts. So this first experiment here shows a classic experiment from Barsalou and colleagues, where they presented the word piano in various kinds of sentential contexts. Normally, if you think about a piano, you would think about it as making a nice sound, and that's what you find when you embed piano in a sentence like the man tuned the piano. But if you embed piano in a sentence like the man who lifted the piano, now you would assume that different kinds of resources are going to be assembled to think about moving a piano where sound's not relevant, but now the weight is relevant. And they demonstrated that this is true with a nice memory paradigm by showing that different kinds of cues help retrieve memories of the sentences that fit with the kinds of features that became active and that were relevant for the original context. We did a similar kind of experiment with concepts like basketball. So normally, if you think about a basketball, you don't think about it as floating. But if you embed basketball in a sentence that describes using a basketball as a life preserver, now you've situated basketball in a way where this property is relevant, and so the situation brings out this particular property. Recently, there's been a flurry of articles where people have argued have again championed this theme, sort of brought back sort of theme from a couple decades ago, arguing that all meanings when words are processed are dynamic. You never represent the same concept twice. These are articles coming from both behavioral literatures and neuroscience literatures, all taking somewhat different perspectives, but they all are consistent on this idea that meaning is situated, reflects the situations in which words are processed. This last example has to do with the categories that people use in daily activities. The best way to demonstrate the idea is with an example. So if I show you these four things and ask you what category they belong to, most people struggle trying to figure out what the category is. But if I give you relevant situational information, you can very quickly establish that this is the category of ways to escape the mafia. There are lots of other categories like this. They're ubiquitous. I have a linguist friend who's now studying them and just finds them everywhere in texts, online corpora. But some other examples would be that when you travel, you have to generate the category of things to pack in a suitcase. If you're going on a diet, generate the category of things you eat on a diet. But the idea is that many categories we use on a daily basis only emerge from sort of organizing your brain in a way that essentially assembles resources for processing a situation such that these kinds of categories become apparent and relevant. Okay, so to summarize what we just covered, we assume that the representation of situational experiences become established in memory as situated conceptualizations. At a given point in time, the external and internal situation cubes a situated conceptualization from memory, which is then applied to the current situation, kind of reactivating a set of resources that are relevant for that situation, and then producing pattern completion inferences that support intelligent action. What I want to explore in a little bit in further depth next is the nature of of what happens in this stage when situated conceptualization becomes active and starts generating inferences. And the argument here is that what happens is that the brain is generating multimodal simulations to deliver the inferences and the suggested actions that would be relevant in this situation. So this slide summarizes what I mean by multimodal simulation. So imagine you see this object. The idea would be that the brain activates resources that would be relevant for processing, such as visual resources in the ventral stream for processing how the object looks, areas of the auditory cortex for processing how the object sounds, perhaps resources in the motor system for interacting with the object and so forth. But the idea is that whatever resources are relevant become active. If you saw food, a different set of resources would become active. Additionally, once these resources become active, they're integrated via association areas that are superimposed on memory. And finally, we would assume that because we're humans, for many of these patterns that we establish, we associate words with them, such as the word dog for this particular pattern of resources. We further assume that over time, as one experiences many instances of the categories, this process repeats itself over and over again, such that an increasingly established network of areas becomes associatively distributed throughout the brain that represents this kind of thing. So you can think of this as soft assembling of resources and sort of developing a well-established sort of system, so that whenever you see this kind of thing in the future, you just pull all this stuff up and it adapts you to interacting with this object. So for example, if you, after establishing a distributed network for dog, you hear the word dog, but there's no dog present, that what this account proposes is you activate this distributed network, you drive it into one particular state of infinitely many, and this state that the network is in represents a dog on this occasion. We refer to this as simulation because we argue that the brain is simulating the state that it would be in if it were actually interacting with the dog. There are many caveats to make about the notion of simulation, some of which are summarized here. First of all, as I mentioned a moment ago, we assume they're produced dynamically, that these networks produce an infinite number of simulations. Very much like the idea that I described earlier, that there's no single cognitive system. The brain just adapts itself to situations. We believe the same thing about concepts. There's no fixed concept of a dog. Instead, you have this network which produces infinite representations that are adapted to the situation you're in. We assume that these simulations are often partial, not necessarily critical, that they're often unconscious, and that when they do become conscious, that's when you experience imagery, but we assume that they often run without much awareness. We assume they can take the form of exemplar specific representations of the category or abstractions, sort of high-level summaries of them. We don't assume that this is the only mechanism for conceptual processing, and we assume that there are strong biological constraints on this process. One other thing that I want to say about this approach to representation is it offers a different way of thinking about symbolic operations. For decades, one of the central themes of classic theories of cognition is that the brain is a symbol processing system. It doesn't process sort of holistic images. Instead, it processes things symbolically. And I agree 100% with this. I think the brain is a symbolic processing engine. Where I disagree with classic theories is classic theories would argue that these symbolic processes are implemented via logical and linguistic kinds of mechanisms, where I increasingly believe that they're implemented as simulation mechanisms. And so I've written some papers that sort of offer accounts of how simulation mechanisms can produce symbolic operations such as type token binding, conceptual combination, and recursion. I'm not going to say much more about these, even though I will show you one empirical result in a moment, but I just want to make the point that the simulation approach offers, I think, a very different way of thinking about the symbolic nature of human cognition. Okay, so in the remainder of my time, I'll briefly go through a few examples of evidence for this idea that simulation is a mechanism for representing inferences coming out of this sort of situated adaptation process that I described earlier. I'll start again with eating semantics. Again, just to review this earlier experiment, what it shows is that when you see a food, you activate a situational pattern associated with it, and you produce inferences about it, and these inferences are running in the taste and reward areas. And these are simulations. I mean, you're activating the same or at least similar areas that would be active if you were actually, in this case, eating the food. This slide summarizes a review that we recently wrote, where we started with a brief review of literature on what happens in the brain when you actually eat something, essentially when that liquid is dripped into your mouth. And this is a network that Kay et al. Constructed based on these kinds of findings, which has sort of a dorsal reward pathway and a ventral reward pathway and a dorsal control pathway. And so this would characterize what the brain does when it actually tastes something. And then we reviewed the literature on food cues when people look at food pictures and then not actually tasting something. And basically what we found from reviewing the literature was exactly the same areas that become active when you taste something, become active when you generate a state in response to food cue. So I think this offers, again, strong evidence that the brain is running simulations in order to represent the meaning of a food to a person. This is a really nice study from a group in Spain, a very simple experiment where they presented them with words for foods and matched words for non-foods, looked at the areas that became active for the foods, and basically the same areas that I just showed you associated with eating become active when you hear a food word like chocolate or coffee, demonstrating that food semantics are essentially simulating many of the same areas that are active when you actually taste a food or see a food picture. I'll next go through a couple of examples from visual semantics, and I'll start with work that did the former student Ling Ling Wu. Sort of the intuition behind this experiment has to do with inclusion, and the idea that when you see an object, that the features on the surface of the object, so like when you look at this lawn, the features on the surface of the object are salient because they're unincluded but the sort of the features of a lawn that are below the surface, like dirt and roots, because they're occluded, they're not very salient to you. And so it follows from a simulation perspective that if you give people the word lawn and you ask them to generate features for it, what they should do is simulate a lawn. And if this account is true, they should generate unoccluded features more often than included. So we would expect to see green blades generating these features more often than dirt and roots. We had another group of participants who was asked to generate features to noun phrases, such as rolled up lawn. So we used the same nouns, but now preceded them with what we call revealing modifiers. And the prediction here was that if you're representing a rolled up lawn with a simulation, now you've unoccluded features that used to be occluded. They may be very salient. And so now you should produce roots and dirt much more often than you did for lawn alone. And that's what we found. So over here on the left, these are the results for the nouns. The blue bar is for external features, unoccluded features like green and grass blades, generated twice as often as included features like dirt and roots. But in the noun phrases, both novel and familiar, when you proceed words like lawn with a revealing modifier, now the originally included features like dirt and roots become produced much more often, consistent with the idea that people are running simulations to represent the meanings of these words, of these conceptual combinations. And again, this I meant to point out that this illustrates how the sort of the simulation view can explain things like conceptual combinations, or at least contribute to it. But again, the idea is that the visual features associated with these words and phrases are coming perhaps from simulation. This next experiment comes from someone who's done, I think, a lot of really cutting-edge work recently on simulation. Marcos Ostark and Bob Kudig at Nijmegen Max Planck Institute. Gary Lupien has also done similar experiments recently. This work uses flash suppression to demonstrate the presence of simulation. What they do in these experiments is they present people with a word, either a concrete word like chair, an abstract word like curiosity, and they ask them, different experiments are different tasks, but in the first experiment the task is to say whether or not the word is concrete or abstract. And what happens is that half the time flash suppression occurs and half the time it doesn't. And what flash suppression is that you see Mondrian masks like these flashing by 1 every 100 milliseconds until you produce a response. And what work in vision science has shown is that when you flash these sequences of Mondrians at this rate, it interferes with low-level visual processing associated with edges, color, and orientation. And so what they predicted was that in a task where visual features might be relevant, such as saying whether something's concrete or abstract, that if simulations are taking place to represent the meanings of the word so that you can determine whether they're concrete or abstract, the flash suppression should interfere with the presentations of concrete words and establishing whether they're concrete or abstract, because you're essentially wiping out an important part of their semantics and low-level vision. And that's exactly what they found. These are the results for the first experiment. I know the font is small. Over on the left are abstract words, and on the right are concrete words. The blue bar is when flash suppression occurs, the red bar is when flash suppression doesn't occur. And the important thing is that there's a significant interaction here. The flash suppression is having a much more detrimental effect with concrete words and for the abstract words, and they argued that this is because the flash suppression is interfering with simulations of the concrete words that are needed to determine the concrete. And two other experiments where the task was lexical decision and determining whether the word was a noun or adjective with the same words, there was no interaction. And they predicted this lack of an interaction because they said visual features aren't relevant for these tasks, so they don't need to be activated, and therefore flash suppression don't have an effect. This next set of studies focuses on a specific kind of visual information, color, and looks at the simulation hypothesis with this kind of information. This is an experiment, again, that was done with Kyle Simmons and Alex Martin, Ken McRae, and a few other people. And basically, the way that what this experiment asked is that when you get a color word like white, yellow, red, do do you represent it with a simulation that invokes color areas of the visual system? And those areas would be areas that are shown in the slide. So you're looking at the bottom of the brain, the back of the brain is down at the bottom. This is essentially the ventral stream. And you have areas of the lingual gyrus down here in the posterior part and of this processing stream, and then areas of the fusiform. The top, a lot of people think the fusiform areas are involved in sort of classifying colors, whereas the earlier lingual areas involved in producing color qualia. These areas are not dependent on language. You see the same areas active in monkeys who are processing color. And so our question was, if you have people processing color semantics, do they engage these areas? And the way we did this is we had people perform a property verification task. They would get a word for an object, and then a color. They would have to say whether the color was true of the object. Again, we used this catch trial design, and we isolated the activations for the color words, removing the activations for the object words. And again, the question was, would we see activations in these areas? And that's exactly what we found. So the blue areas are areas that are activated by the color words relative to the motor properties. And this red area represents overlap for the color words with the color processing area. So we found activation in the fusiform area of the color processing string, suggesting that to represent these color words, people were running simulations in the visual system. A number of other studies have shown this. One of my favorites is from Sharon Thompson-Schill's lab at Penn. And what's really, I think, significant about this study is that we didn't find activations in these lingual areas. And so they wanted to see if they could get activations in these areas. And so what they did was they argued to get activations in these areas, you need to have a harder color test that requires sort of more detailed simulation to get to the point where you're actually generating qualia. And so the task that they used was to give people pairs of objects like lemon and basketball and ask which of these two words is brighter. And when they did this, lo and behold, they found activations in the lingual gyrus. So again, they're just getting colored words, and they're activating areas that are associated with color processing. This last study is a more recent study where it's a very different kind of study where the experiment assessed people's color knowledge about various kinds of colors of 100 or so things. There are large individual differences in how much people know about what color various things are. And basically, you're looking at sort of using a race resting state method I'm not going to go into any detail about. They showed that the areas that became more active in this resting state paradigm, they correlated, whose activations correlated the highest with color knowledge were again in this ventral processing areas in the fusiform and the lingual for processing color. So there seems to be increasing evidence that when we represent color semantics, we're using the visual system. The last thing that I'm going to talk about are spatial semantics. And the idea here is that many words and sentences that have spatial meaning refer to spatial situations. Like drop implies kind of a vertical direction of motion, whereas push implies a horizontal direction of motion. Sky maybe directs your attention up, ground directs your attention down. And so one possibility is that when you encounter language like this, it induces spatial simulations. And there's actually a lot of great work that bears on this. Some of my favorite work comes from here, Merced, done by Team Matlock, on fictive motion. And the idea is that when you read a sentence like the road goes through the valley, what you actually do is you simulate motion through some representation of the valley being constructed. And the ingenious way that she tested this was to manipulate the preceding sentence. So one group of participants read the sentence, the valley was flat and smooth. A different group of participants read the sentence, the valley was bumpy and moving. So the idea is that you've got these different ideas of what the valley was like, and now you're reading about the road running through the valley, and you're simulating motion. And you're going to simulate very different motions as a function of whether the road is going to a smooth valley or a bumpy valley. And the prediction was it should take longer to read this sentence after the bumpy and uneven sentence than the flat and smooth sentence. And that's what she found, a third of a second longer to read exactly the same sentence when you believe that it's bumpy or rough. And she found the same kind of effect across several experiments that were paradigms and later with eye movements as well. So indicating that people are running spatial simulations as they're understanding language. This next experiment was done in the collaboration with Marcus with his student Daniel Richardson, I guess, when we were still at Cornell. And basically, it sort of utilizes the same intuition as the previous experiment. Participants read sentences like "the girl rushes to school," which implies horizontal motion, or like sentences like "the ship sinks in the ocean," which implies vertical motion. And so they would listen to these sentences over headphones, and then a square or a circle would be flashed at one of these four positions, and participants would have to press a button to indicate whether the stimulus was a square or a circle as quickly as they could. And this came immediately after the end of the second, so that sentence was a little bit of random jitter. And the prediction was that if people were simulating the spatial trajectory for the sentence, that this would interfere with the perception of an object on the same axis of motion. And that's exactly what was found when people read sentences implying horizontal motion. They were slower to detect the target on the horizontal axis, whereas when they read sentences about vertical motion, they were slower to detect targets on the vertical axis. This is a study that Zach Estes and I did subsequently, a very similar idea, where we simply presented a word that implied something that would be found up high versus low, like a hat or shoe. And then we presented an X or a 0, either at the top or the bottom of the screen. And we predicted that when the critical stimulus, the target, the X or 0, fell at the location sort of predicted by the concept in the middle of the screen, we would observe interference because the prime would essentially produce a simulation that would interfere with detecting the target at that position. And that's exactly what we found, that people were slower to detect the targets at the expected position than the unexpected position. There's recently been a Psych Science article that failed to replicate this. And so it also included a very sketchy partial meta-analysis that just selectively said a few things. So in our reply that just came out, we published a much more complete meta-analysis of the literature in this area. And basically, what we found from this meta-analysis is that this effect depends on certain conditions. You only get this effect when you access the semantics of a word. If you don't access the semantics of a word, you don't get this effect. And this makes sense because these spatial features are kinds of semantics. And it's possible under a lot of conditions to process a word without activating the semantics. And so a lot of these failures to replicate were occurring because semantics just probably weren't being activated. The other condition that's crucial is that once you've activated semantics, the target has to appear within 400 milliseconds. Otherwise, the interference dissipates. What actually you're left with is attention where the target is, and you actually see facilitation. And that's what we found in this meta-analysis. So at long SOAs, you actually see a very slight facilitation effect. At shorter SOAs, if you don't achieve semantic processing, you don't get the effect. Basically, the orthography of the language being used is critical. So languages like Italian and German, they're so predictable and so regular that often people, there's a literature on this, one of which done by the people who failed to replicate is showing that in these languages, you often don't get classic semantic priming effects because people don't have to activate the semantics. Only in a language like English, which is irregular enough that people consistently activate semantics, do you get this effect. And if you use English at a short SOA, you get a very substantial interference effect. The other interesting thing that came out of this is that if you add semantic context, you double the size of the effect, consistent with the idea that this is a semantic effect. Okay, I'm going to tell you about one last study and then how to stop. This is another study, this is another experiment from Marcus Ostaric's dissertation that I really like. I think it's such a clever experiment. So it's going to use fMRI, it's going to use very similar task to the one I just showed you. You get a word in the middle of the screen that either refers to something up high or low. And so in the scanner, participants are getting these words like bird and shoe, and they simply, and the task is to say whether they're concrete or abstract. After they do this task, where they're just saying whether these words are concrete or abstract, they do a second task. And in the second task, they watch a cross go up the screen or down the screen. And so then they're going to image their brains as they're viewing the visual motion of this cross. And then the really amazing thing they do is they train a linear support vector classifier to identify parts of the brain that can distinguish upward versus downward motion in the moving stimulus. So there are areas all over the brain that are sensitive, that discriminate between upward and downward motion. And then the key question is, if you take the brain areas that are associated with upward semantics and downward semantics, can you identify, if you take the brain data from this task, can you identify in each trial whether people were reading an upward word or a downward word from the patterns established on this visual motion test? And you can. There are areas all over the brain, various spatial and motor processing areas that can decode whether you're looking at an up or down word. Again, I think clearly demonstrating that when you read words with spatial meaning, you're activating the spatial meaning. Okay, so I'll wrap up. I began by suggesting that there is not a situation-independent cognitive system. Instead, I argued that as the situated action cycle runs, it assembles the resources it needs in the brain and the body to implement the 5 phases of the situated action cycle, and then it superimposes this assembly of resources on the cognitive system to support situated action in future situations. I also suggested that as different individuals perform the situated action cycle differently in different situations, they establish different populations of situated conceptualizations that essentially adapt their brains and bodies to the kinds of situations that they normally find themselves in. Finally, I argue that once a population of situated conceptualization becomes established in a person's brain, that they then become active to support intelligent action in relevant situations. And that when a situated conceptualization becomes active, it essentially assembles the resources that are needed to process, implement the situated action cycle in that situation. And finally, I briefly reviewed evidence that cognition adapts itself to situations in this manner, and that it implements sort of inferences about the situation without relevant action in it via multimodal simulation. Clearly, much remains to be developed within this general framework, but my sense is that it has promise for helping us achieve a deep understanding of the algorithmic mechanisms of cognition. Thanks for your attention.